Hello everyone, welcome to YouTube channel MS Chem Insights by Dr. Aksa Habib. Today I am going to discuss the fourth part of catalysis, that is catalytic deuteration. Catalytic deuteration is a chemical process that involves the replacement of hydrogen atoms of organic or inorganic compounds with a heavier isotope of hydrogen, that is deuterium, in the presence of a set of catalysts or single catalysts, which helps to facilitate the reaction by increasing its rate, efficiency and selectivity. Catalytic deuteration finds its applications in nuclear magnetic resonance spectroscopy. As you know, NMR activity is determined by the presence of nuclear spin quantum number. So the elements that have nuclei with a non-zero spin quantum number are considered NMR active. The protium, which has only one proton in its nucleus, its spin quantum number is 1/2, which makes it NMR active because it absorbs and emits radio frequency radiation of externally applied magnetic field that helps in generation of NMR signals. On the other hand, deuterium, which has one proton and one neutron in its nucleus, its spin quantum number is 1, but it is considered as proton NMR inactive in the sense that deuterium does not produce a signal in the same range of chemical shift in which a protium do in a typical proton NMR spectroscopy. Liquid state NMR spectroscopy requires solvents for the solution formation, and the common solvents which are used for this purpose, they contain protium, for example, water, methanol, chloroform, acetonitrile, and dimethyl sulfoxide. They all contain protons, which is NMR active, and it gives a very strong signal in NMR spectra due to presence of large excess of solvent. Thus, the presence of the protons of solvents interrupt in the detection of hydrogen signals of actual analyte or organic compound. Thus, it can mislead or hinder in the identification of analyte due to weak signals of the analyte as compared to that of solvent. So, in order to avoid this inconvenience due to presence of protons of solvent in detection of actual analyte, the protons of solvents are replaced with proton NMR inactive solvent of hydrogen, that is deuterium, which is inactive in the proton NMR spectroscopy. Here is a representative NMR spectrum of one of the compound I prepared during my PhD. Actually, the deuteration of solvent doesn't mean that it's all the protons are replaced 100%. The deuteration may be 90%, maybe 95%, but 100% deuteration is almost impossible. So in this NMR spectrum, you can see the solvent peaks due to presence of acetonitrile and water, which are used during the synthesis and solution formation of this compound. So deuteration doesn't mean that the solvent peaks will not appear. They may appear, but their intensity is not too much higher that they interrupt in the appearance of signals of protons of our desired compound. Here is a mechanism of catalytic deuteration, which involves the replacement of hydrogen of benzene by deuterium, which occurs in a series of alternating reductive elimination and oxidative addition steps in order to generate the deuterated benzene, which is an NMR solvent in the presence of a suitable catalyst, for example, the catalyst containing transition metal tantalum. In the first step, this catalyst undergoes reductive elimination by dissociation of hydrogen, thus producing a 16 electron species from 18 electron species. In the second step, this complex undergoes oxidative addition, which involves the addition of benzene in order to generate 18 electron species. In the third step, this compound undergoes reductive elimination by removal of hydrogen in order to create a space for the incoming deuterium molecule, which is added in the next step of oxidative addition. In the next step, which is a final step of first cycle of deuteration, that is reductive elimination, which produces unideutyrated benzene and a deuterated catalyst. As you know, the benzene contains 6 protons which are to be replaced with 6 deuterium atoms. So this cycle will be repeated 5 times in order to generate fully deuterated benzene, that is C6D6, and the deuterated catalyst will be released in each cycle. This was all about the catalytic deuteration. If you have any question or query, you may drop me an email. The email ID is given in the start of this lecture. Thank you very much for your attention.